So why did we start our discussion with direct sum orientation? That's because once we have defined the concept of direct sum orientation, then we have a new way of constructing orientation. The idea is that, say, if we are given an orientation on this direct sum, and we are also given an orientation on V, then we have a natural induced orientation on W. It's the unique orientation making the orientation here into a direct sum orientation of V and W. For example, let's look at the closed disk. I'll write that by d bar. Given a point P on the boundary of this closed disk, we can think of the tangent space to the closed disk at P as the following direct sum, as the direct sum of the following two spaces. One is the tangent space to the boundary circle at P, and the other one is the normal space to the boundary circle at P. So now suppose we have some orientation on this full tangent space and also on the normal space. Then we will show how to deduce the induced orientation on this tangent space. Alright, so let's assume the orientation on this tangent plane is the counterclockwise orientation. And on this normal space, let's choose this orientation, the one represented by an outward pointing normal vector. Now let's see what should the induced orientation on this tangent space be. Is it going to be this direction or this direction? How can we tell? Well, we have defined the induced orientation here to be any orientation such that the direct sum orientation on this is exactly the orientation given on this plane. So it's this counterclockwise orientation. Thus, if we call this vector the vector that represents the orientation on the normal space, if we call it n, and if we call the vector that represents the orientation on this tangent space v, then n comma v should represent an orientation on this tangent plane, this big tangent plane, i.e. n comma v should represent the counterclockwise orientation. And so that means that v must be in this direction. And thus that is the induced orientation on this tangent space. In particular, this actually gives us a way to define boundary orientation. This is because at any point P on a general manifold with boundary, we still have the direct sum decomposition into the sum of the tangent space to the boundary of M at P and the normal space to that. So just as in the case of the closed disk, if we know an orientation, if we are given an orientation on this tangent space and an orientation on this normal space, then we get an orientation on this boundary. Actually, by convention, there is a default orientation on this normal space. So what's this default orientation? Well, the first thing we need to observe is that this normal space must have dimension 1. And why is that? To see why this dimension is 1, we need to remember the definition of manifolds with boundary. Let's say our manifold has dimension m, then that means locally it looks like the upper half space hm, right? And the upper half space hm was just defined to be the subspace of Rm, consisting of points with the last coefficient being greater than 0. In particular, the boundary of this upper half space is cut out by this coordinate function xm. So it's cut out by a single function, and thus it has codimension 1. So the tangent space to the boundary here also have codimension 1, which means that this normal space must have dimension 1. In particular, an orientation on the normal space can be represented by just a single basis vector. We'll choose the default orientation on the normal space to be that corresponding to the outward pointing unit normal. Well, we know what it means for a vector in this normal space to be outward pointing normal vector in this case, right? In this case of the upper half space. But how about on a general manifold M? Again, a general manifold with boundary is locally looks like this upper half space. So we can just carry this orientation over here. We'll denote the unit outward pointing normal vector by NP. Alright, so that's the default orientation on the normal space to the boundary. Now what's the induced orientation on the boundary? Well, as before, so if we have an orientation on M, in particular that means we have orientation on each of these tangent spaces, then there is unique induced orientation on each of these tangent spaces to the boundary. It can be explicitly described in terms of the orientation map as follows. So an ordered basis of the boundary has orientation number 1 if and only if the oriented basis obtained from it by adjoining this NP to the beginning, viewed as the basis of M, has orientation number 1. I'll put it differently, slightly differently. This ordered basis represents an orientation on the boundary if and only if this induced ordered basis on M represents the given orientation on M. Alright, so that's the definition of the boundary orientation. Next, we're gonna look at a specific example of this, the boundary orientation on a homotopy space.